Good morning.
Good morning.
Morning.
All right, let me get myself situated here. Okay, I have the module for this week published except for the discussion page. No, I have the discussion page, except for the assignment. And so I'm about to add that. How come I think I needed to add the discussion page? Oh, a question page. Yeah, so I'll add the discussion, which is a question page. There we go. And then add the assignment. I have them ready. I just need to post them. And this assignment is available all week, so you have a week to work on it. It's due, yeah, the 21st. Your other assignments are being graded, and Michael, this is his first time grading for this class, so the first one took about I think almost a week to get the grades back, and he'll pick up steam as he goes through and gets more familiar with stuff. You guys took a survey last week about how the online courses are going, and the responses were good. I was pleased that overall we seem to be doing okay. You know, this is an experiment for me too, so it's really good to get information and get feedback. There were a couple comments though that I wanted to address. One was that I should be more consistent in publishing announcements, like a check-in announcement, and I agree with that comment. I think that's a good thing, and what I'm getting myself to do now that I'm getting into a schedule is every Friday, what I want to do Friday afternoon is post for y'all what the next week looks like, so that you have an understanding of what to expect a week ahead of time. And then if anything unusual comes up, then I'll post another announcement. What I don't want to do is bombard you with announcements. It's like, oh God, here's another thing from Garfield. I want to make sure that what I send out is actually useful information and not just me talking. And then the other comments were to the question, do you have an opportunity to interact with the other students? And that was where we got the largest answers of no's. And I agree with that assessment, and I don't really know what to do about that, because here we are in our separate little boxes on Zoom meetings instead of in the same classroom or in the hallway, which is where you get that normal contact. And you start to form relationships where you're discussing the course material or whatever. So I think the online format is tough. Now, what I've tried to do, how do I do this? There we go. Just to remind you, we do have discussions in the course, and every module has its own discussion section, but then I've also asked these different questions, language, grammar challenges, what is computation, that kind of thing. And that's the reason I put those there, is to try to give you guys some opportunity to talk to each other. My goal would be that you would ask a question, right? So if you had a question about PDAs, you would ask a question in that discussion section. And ideally, in a perfect world, other students could chime in and give their thoughts on what the answers might be. And that would be a way for you guys to interact with each other. I don't know how realistic that expectation is. It's not quite the same, is it, as sitting down in the same room as somebody, or you happen to sit down with someone in a lab or at lunch hour or something like that, and and you ask, hey, are you having trouble with question number 2, and that kind of thing. So It's not quite the same. And plus, I think when people have questions, it's a natural human tendency to be a little bit shy about advertising that you didn't know something. And, you know, we have to overcome that in order to make those discussions work out. If you guys have better ideas, please let me know. If you guys think that I should stop putting a discussion section in each module, please let me know. What I need to do is see it from your point of view and see if we can improve the cohesion of the class, basically. So all of you guys that participated in that, I really appreciate that. I did not send an announcement out specifically about that because typically when the university wants you to fill out a survey, you already get enough emails and you get enough interruptions, and I didn't want to be yet another. Same with the end of the course surveys. I'm going to remind you once or twice at the end of the semester to fill out your online evaluations. Yes, you do get, I do bribe you with extra credit for that, but you know, we all know you're going to get 100 emails from the school about filling your online end of the semester evaluations. If what I'm saying is way off the mark from your personal experience, by all means, you can talk now, or, you know, if you want to contact me privately, that's fine. Let's see. How do y'all feel about stack machine? Not stack machines. The finite state machines. Who's willing to volunteer that they are comfortable or uncomfortable with them from the previous module?
It reminds me.
Pretty comfortable.
Max, was that?
Yeah, I feel comfortable because it reminded me of CS332.
Yeah, so yeah, you guys that took CS332 last semester, you know, hopefully the summer didn't drain all that knowledge completely. Yeah. Who else spoke up? I didn't catch you.
I would say, yeah, I feel pretty comfortable with it as well.
Okay. You took CS222 also though last semester, right?
Yes, sir.
Yeah. Okay. If people are not comfortable enough, then what I'll do is I'll go through this material today, but on Wednesday, we can go back and still talk about finite state machines some more. The more comfortable you are with finite state machines, the easier the transition is to the stack machine. So don't let your hesitancy to acknowledge that you're really not there yet on finite state machines shoot you in the foot for this section. Okay. So this is the next model of computation. And in order to go fully into this topic, I'm going to say we need 3-4 weeks, something like that. So basically, my goals for this is that you know what these things are, that you can create them for simple situations and understand how they work. We're ignoring some aspects of this that if we had a course that was completely devoted to models of computation, and they exist, then we would go into more details on the different variations that you could have on a stack machine and the variations that you would have on a finite state machine. So be aware that I am not giving you the full story. I'm giving you what I hope is a good introduction to the topic. As usual, when you're done with the module, go back to these outcomes and convince yourself that you really got these outcomes. Okay, same kind of slides we had for finite state machine. They have theoretical value because we're still asking that question, what can a computer compute? And we're not going to be able to answer that question fully until we get to Turing machines, but we're on the way. We're on the road, and we're building ourselves up to Turing machines. It's just another math model of computation, and they are stronger than finite state machines because they do have memory, the stack. Now I'm going to use stack machine, PDA, push-down automata as interchangeable terms. You may find other authors or instructors who maybe want to make a distinction, but I don't see that it's useful for this class. Okay, in addition to theoretical value, they have practical value. All real-world programming languages are context-free, and these match up to the context-free languages, which means that your compiler, remember the first thing your compiler does is it parses your program and says, is this program legal? If I wrote a Java statement, is this a legal Java statement? You know, it's literally asking the question, are you in the set of acceptable Java strings or not? And it is a stack machine that performs that job. And when we do the section on compilation, I have an example that we used to have a textbook for this class, and it came out of that textbook. I really like the example. It shows you how the stack machine works to parse a simple statement in a programming language. It's also used for scheduling tasks. Now, some of you folks have probably had CS315 by now, because a lot of times people wait to take this class till they're about to graduate. And if you have taken CS315, any of you guys taken CS315?
I'm taking it right now, and I've studied some of it over.
Yeah, I'm taking it now.
Okay, all right. And you know you're going to study stacks in there as a data structure. Or didn't you know that? You should study stacks in there as a data structure. So anyway, stacks are used as a real world tool to do task scheduling primarily. And typically, you know, y'all are at least familiar with the idea of a stack, hopefully. The idea of a stack is that you can put in a bunch of data, but you can only look at one element at a time. It's literally like stacking boxes on top of one another. You can stack a bunch of boxes, but if you want to actually use a box, you better take the top one off the top of the stack, not one off the bottom, you know, like Jenga, right? You don't want the Jenga situation to happen. So a stack is a specific data structure where you can add and add and add, but what you're doing is you're adding these items on top of each other, and you only have access to the topmost item, which is the last element. So I have another slide where we talk about that a little bit more, but what that means is when you're scheduling tasks, if you think about how you go through and say, okay, here's what I have to do. I have to do something, and I break it down into tasks. Then you can think of it in terms of, okay, but in order to do that, I have to do this. In order to do that, I have to do that, you know, that kind of thing. So it's like, okay, I'm changing the roof out in my shed where I store feed and grain for our horse. So I said, okay, I want to change that shed out. But in order to do that, I need to buy plywood for the roof. So that goes on top, right? Before I get into nailing it down and painting it, it's like I got to buy plywood first. So that goes first. And then the next one is, okay, now I need to cut the plywood. Oh, wait, you have a battery powered saw, and the batteries, I didn't realize the battery wasn't charged. So I need to charge the battery. So that goes on top of the stack. See, so what happens is you can put tasks on top of stacks. And then as you remove the task, then you just keep going down the stack. We are going to consider these push-down automatas, just like we did with the finite state machine, as language recognizers. Are you in the language or not in the language? Chomsky one more time. This is the context-free definition. And Chomsky one more time, reminding you that context-free and stack machines are equivalent. The stack machine is the model of a computation that can recognize context-free. So here's a quick question. Can a stack machine also recognize regular languages? What do you think?
I'd say yes.
You'd say yes. Why are you right?
Question.
Well, let's see. A stack machine is a stronger model of computation than the finite state machine. And if it's a stronger model, it can do as much or more as a finite state machine. So since it can do more than the finite state machine, it can do as much and more. And if it can do as much, then it can do the same as a finite state machine. So yes, in fact, my second example is actually a regular language. But instead of solving it with a finite state machine, I solve it with a context, with a stack machine, which of course is wasteful, right? In terms of resources, you always want to go to the weakest model, but it's an example. Okay. Yeah, question?
Just saying, okay.
Before we move on, this context-free versus context-sensitive, I wanted to clear up what those terms meant. What context-free means that we have only a single non-terminal on the left-hand side, and what that really means is, I don't know how I can highlight this very well. If I have a set of 3 production rules like that in my BNF form, whenever I see a capital A, I am free to choose any of those 3 options at any time, no matter what. That's what that means, right? That's the way we've been using it. But in a context-sensitive language, I might have a rule like this where I only have the single non-terminal A on the left-hand side. But I might also have a rule that looks like this, where I say A, capital A. Now the lowercase a's are symbols in the alphabet. So what am I saying? I'm saying that I can only use the rule where, technically this should have been, I don't want to destroy any terminals. I can only use the rule where I can basically replace this non-terminal A with the non-terminal AB. I can only use it if that non-terminal A was preceded by 3 A symbols. That's the context. What you're saying is you can only use these rules in particular context. Now that may seem like it's actually a restriction on the power of the language, but we'll see that it's not. Or I'll give you a common sense definition that it's not. So up here in the context-free language, because context didn't matter, I could always go from capital A to capital AB. And here in this language, I can only go from capital A to capital AB if I'm preceded by 3 A's. That's the context. Which basically what that means is you can have more if-then conditions. And if you can have more if-then conditions, you really can do more of a description of different situations. And I'm going to give you an example from games. How many of you guys have ever played have taught someone to play a game? And I'm going to use a card game. And you say, okay, in this situation, it's a good idea to play your ace. And then the person that you're teaching plays their ace and they lose. And they said, you told me in that situation play the ace, or you told me it's always a good idea to play the ace. And you said, well, wait a minute, that situation wasn't the one that I was talking about because there was this other factor going on. There was something else was going on. You know, somebody had already trumped the trick or something like that. And if somebody already trumped the trick, then playing your ace is a waste of time. What are you really saying to them? You're saying, if this is the context that you're in the game situation, then you should do this. But but in a different context, you should do something else, which means that you're able to give them a more rich description of how to do good gameplay. Football season, pro football season started over the weekend, college football season. And, you know, sometimes teams on 4th down choose to punt, and sometimes teams on 4th down choose to go for it. What makes them make that decision? Context. Context. They don't just always, you know, flip a coin and make that decision. So that's why there's more. I'm hoping what I'm doing is giving you just a folksy argument as to why context sensitive actually gives the language more power. So we're at context free still right now. I just wanted to clear up what those terms meant. So we're still in context free, we're still in PDAs. Okay, basic definition. It's just similar to the finite state machine. Mathematical device to recognize certain languages, accepts all strings in the language, rejects all strings not in the language. Sometimes you'll hear me say it can accept all and only. It should accept all and only strings in the language, meaning it accepts all the strings in the language, but only strings in the language. Therefore, it should reject all the strings not in the language. Just like with the finite state machine, each language can have many PDAs, an infinite number of PDAs, and you know, most are trivially bloated. We're dealing with deterministic PDAs still. I'm going to cheat that just a slight bit later on for ease of presentation. But deterministic, remember what deterministic means. Deterministic means that for each situation you could possibly imagine, you have exactly one action that can be taken. which means that in any situation you're in, you can determine immediately what the one thing you're supposed to do is. In the context of predicting what happens, if a system is deterministic in every possible situation, then you don't even need to run the actual situation. You can predict or determine ahead of time what the result will be. So that's what deterministic is about. Non-deterministic things are like dice rolls, or where you have options. You can do this or you can do that, and there's no controlling factor as to which of those options you would take. So we're going to deal with deterministic PDAs. Non-deterministic finite state machines and PDAs do exist. And again, if this was a course solely about models of computation, we would have talked about those. But I just want to give you an introduction to PDAs. Oddly enough, some of you guys are going to take SE410, and you may encounter this again then. You will definitely encounter finite state machine and PDA push-down autonoma type models in SE410, or you should. A non-deterministic finite state machine does not give any more power to the finite state machine. Everything you can describe with a non-deterministic finite state machine, you can describe with a deterministic one. Oddly enough, with a PDA, that's not true. You can actually describe more things with a non-deterministic PDA than you can with a deterministic one. It still falls into the category of context-free. Anyway, we're going to deal with determinism. Now, what's the informal definition of the PDA? It's just a finite state machine with a stack at it. It's that simple. Some of the details and the notation starts to get ugly here, so I don't want you to be distracted by that. You can always go back to that. It's just a finite state machine with a stack at it. Now, that's easy to say, but now we have to take into account, what does that mean? Well, it means a couple things. It means I'm traversing the finite state machine just like I was before, but along the way, I'm also making notations on the stack. And if I'm making notations on the stack, that means I'm writing symbols on the stack. Let's go back to that kind of language. Okay, if I'm putting symbols on the stack, do the symbols that I may use to make up my language, do those have to be the same symbols that I put on the stack? They do not. So in order to account for that, we're going to add an additional alphabet called gamma, capital Gamma. So now we have two alphabets, sigma, which is the symbols that are used to make up the strings of the language, and gamma, which are the symbols that are used to keep track of what's going on the stack. We also have to figure out how we know that there's an empty stack. Remember, computation is a mindless exercise. How do you tell something with no brain that it's reached the end of the road, that it's reached the bottom of the stack? You can't. You have to have a special end of stack symbol. You guys that took C already knew this. Don't you have to worry about end of file marker in C when you're doing file I/O? Why did you need to tell the computer it was the end of the file? Because the computer's so stupid it doesn't know. So in order to add the stack to the finite state machine, we have to add two things, the stack alphabet and the end of file marker, or the bottom of stack marker. Yes, you can have the stack alphabet and the language alphabet the same, other than the end of, other than the empty stack marker. Yes, you can have them the same. In my examples, I chose not to, because I want to have a real clear separation between the string that we're processing and what's going on the stack. But that's an artificial thing that I'm doing. Okay. And in order to do the transitions now, since we have a stack, we may as well take it into account when we do the transitions. So our transitions used to be dependent upon only two things. What state am I in, and what symbol from the string am I looking at? Am I processing? What state am I in, and what symbol am I processing, right? That's how finite state machines work. And now we're going to add a third. What state am I in? What symbol am I processing? And what is currently on the stack? And similarly, our output is going to change. It's going to be, used to be just what new state do I go to? And now it's what new state do I go to? Oh, and by the way, what do I do to the stack? And I framed it entirely as the only thing you can do to the stack at that point is add to it. Even if all you're doing is adding the empty string. I'm sure we can find definitions where you could also still remove from the stack. The thing about removing is you can only pop one thing at a time. You can only remove one thing at a time. And when you're adding, you can add strings if you want. So you can add more than one thing at a time. All right, so formally our 5 tuple for the finite state machine, our 5 tuple was Q sigma Q naught F delta. And now we've added 2 things, so we have a 7 tuple. So now it's Q sigma gamma Q naught Z F delta. Q is the set of states, just like we had before. Sigma is the alphabet by which the language is composed, just like we had before. Gamma is a new alphabet that's going to be used for the stack. Q naught is the start state, just like before. Z now is the symbol that represents empty stack. F is our set of final states, just like before. Delta is a transition, just like before, except now we have to modify it to take into account the stack. Do I need to pause for questions? Well, let me pause for questions. Okay. I think the notation is uglier than the actual operation of the machine, quite frankly. It can be tough to design these to convince yourself that you have all of the strings that you're supposed to have and you didn't accidentally allow others to sneak in. But the actual operation of the machines when we do them graphically, I think is more intuitive than notation. I'm kind of a notation fan, so this stuff helps me. But most people are more graphically oriented. All right, so how do these things operate? How do we process a string? Well, just like in a very similar way to the finite state machine. So to process a string, we're going to process the string one symbol at a time from left to right. The machine starts in Q0 and we start with empty stack. We process the string one symbol at a time, left to right. Now, every time we process a symbol, what we do is we remove that symbol from the string. But now we're going to look at whatever's on the top of the stack, and we're actually going to remove it from the top of the stack. And you'll see that in the notation when we start to get to the notation. So we're actually removing a symbol from the string and popping something off the stack. Now I'm going to empty stack symbol, I pop, which is kind of a weird thing because now that stack's really empty, right? And you'll see that I pop, but it is a symbol, so you're allowed to pop. You're allowed to pop that thing. By pop, I mean remove. Right? Every symbol that's processed then results in a state transition, and something may be pushed back onto the stack. And accepted strings are in the language, rejected strings are not. We're going to talk about the acceptance criteria on the next slide. It's a little bit different. I'm also adding a new thing here. And the reason is you really can't, you know, I did not need to add this when we talked about finite state machines, but you really need to add this for PDAs. These are called ADA transitions. An ADA transition represents a transition where no input is processed. So what that really means is you might have a situation, or you now can create situations where when you process one symbol, you actually trigger multiple transitions. The first one being the transition that was due to the symbol, and then the next one is automatically given to you. You know, you draw a circle and you put ADA on the arrow, and the ADA transition happens without any other input. You just draw to the next circle and put ADA on there, and you can now schedule or set up a whole series of transitions. We're still going to keep this as a deterministic system, but we are going to allow these interesting transition without affecting the input or popping off the stack. I don't know that I have any examples in this slide deck right now, but I know when we talk about different sample problems, this is going to come up. I was spending a couple hours last night trying to, or sometime last night trying to convince myself that I didn't need them, but okay. Now, the acceptance criteria is a little bit different than for a finite state machine. Now, remember, the finite state machine, you knew you would accept a string if you ended up in a final or accepting state. And we can still use that criteria for a PDA, but it turns out for the PDA, because not only do we have a set of states, we have a stack, we can choose to accept based on accepting state. Did I end up in an accepting state? Or I can choose to accept based on empty stack. You would not create a machine where you mix them up. It's going to be one or the other. I'm going to use empty stack. So if we do the accepting state criteria, then our machine accepts a string, and if and only if, and here's some, in my opinion, beautiful notation. You may disagree. If we start in the start state, we start with an empty stack, we process string U, and now our result is going to be some state, right? Some state. If we're going to accept based on accepting states, then all we care about is what state did we end up in. So that state has to be one of the elements in the set of accepting states, or the set of final states. And there's going to be something on the stack. And this is how, remember sigma star was all possible strings you could write from the language sigma? Well, gamma star is all possible strings from gamma. So what I'm saying is, I don't care what's on the stack. Anything can be on the stack. So the formal way to describe this accepting state acceptance criteria is, if I process string U, starting with an empty stack, starting in Q0, and what that's going to return to me is two things, a state and a something on the stack. If the state is one of the final states, and I don't care what the anything can be on the stack, then we're good. If we do the criteria, acceptance criteria based on an empty stack, same trick. I'm going to process the string using the delta function. I'm going to process the string starting with an empty stack, starting in Q0. And now I need to have empty stack symbol on the stack. And I don't care what state I'm in. So I can be any state in the machine is fine by me, as long as I get that. And this cross notation, the Q cross Z, if you go back and remember your set theory, that's all possible ordered pairs of a state with Z. Now you can design them to be one way or the other. I'm going to use empty stack. I like empty stack. That's just my personal preference. If you want to do a machine, when I say design a machine, and if you want to do it by accepting state, that's fine. All right, the transition function. As I said before, now we have to take in 3 things as input, and we're going to put 2 things as output. So we need to take in the symbol that we're dealing with. We need to take in, I'm using X to be what's currently top of stack, and we need to take in our current state. And we're going to output, oops, a state transition, and what are we going to push onto the stack? So we're going to output 2 things. One is the transition, and one is the what do I do on the stack. In CEC220, I think you talked about finite state machines there in a different context, but you may have talked about Mealy machines and Moore machines, and I can't remember which is which, but one of them, in addition to doing the transition, you always spit an output. You spit a symbol as output. This is a similar kind of thing. So here we're going to, every transition now has to be defined to do the state transition and do the what did I do to the stack question, which is basically, did I push anything onto the stack? Graphically, they look virtually the same as finite state machines. Start state, final state, those are all the same for finite state machines. Now, since I'm going to accept by empty stack, I'm not going to have any final states in my machines. If you're going to accept by accepting state, then obviously you need some. And now my transition looks a little more cluttered because I have to take into account 2 things show up on the arrow. This is saying I'm in state QI, and if I see an A and my top of stack is 1, that's when I use this arrow. Oh, and by the way, in addition to transitioning to QJ, I'm going to push 1, 1 on the stack. So you can push more than one thing on the stack. You push it on as a string, and we're going to talk about why you do that. Basically what you wanted to do. If I wanted to add a 1 to the stack, I actually have to do this where I do 1, 1. And the reason is if I want to add a 1 to the stack, I've already removed 1 right there. I need to put it back, and then I add 1. So your graph starts to look a little more cluttered because there's just more things sitting next to the arrows. You can write it this way, you can write it this way. I'm not going to freak out about that. And because it's more cluttered, think about this. If I have, my sigma is AB, right? Sigma is AB. And my stack alphabet, let's say, is 0, 1, and $sign being empty stack symbol. How many unique pairs can I create here? Combinatorics question. Well, let's see. I can do A0, A1, $sign, B0, B1, $sign. All right, so I get 6. So I have 6 unique possibilities. If I'm in QI, I have 6 unique possibilities here. And I want to do a deterministic machine, which means, remember in the finite state machine when you had an alphabet of 2 and every one of your states had to have 2 outgoing arrows, 1 for A and 1 for B. Now I need 6 outgoing arrows for each state. And not only is that annoying, it's a visual nightmare. So what I'm going to do here is only show the states that I'm interested in terms of causing the transition. And I'm just going to ignore things that will basically cause me to go to a trash state or that I know will reject the string. And we're going to say any arrow that is not shown, it's assumed it's an immediate reject. Stop processing and reject. Now the reason I can get away with that, because that sounds wrong, doesn't it? That should really make you feel queasy in your stomach that I'm saying that. The reason I can do that is because I could, if I wanted to, take all of those that I'm not showing, dump them into a trash state where all I do is keep adding to the stack, and every time, for the rest of the, no matter what happens for the rest of the string that I'm processing, I just keep adding to the stack and adding to the stack, guaranteeing that I will never get empty stack at the end of the string. Therefore, ultimately, the string would be rejected. So what we're going to do here is say, we're only going to show you these strings that are in the language, and then anything else that's rejected, I'm going to not show you those arrows just to save visual clutter, and it's an immediate reject. Any issues with that? There should be some issues with that. There should be some confusion with that. All right, I know what you're doing. You're saying, let me watch him do the example and see if it clears this up. That's what you're doing. I've done that. Okay, once we get into the graphical form, it actually does hopefully clear things up. Now this works better on a whiteboard, unfortunately, but here I am. The first machine I'm going to do, this is the hello world of PDAs, by the way, is A to the N, B to the N. A to the N, B to the N means that you have a sequence of A's followed by the exact same number of B's, and you cannot create a finite state machine for that. Now, why can you not create a finite state machine for that? Because you have to remember how many A's you had before you start processing the B's, and the finite state machine doesn't have memory. And I hear you saying, but I could do this. If I have one A, I go out, from Q0 to Q1 if I have one A, and then if I get one B, I go from Q1 back to Q0, and then I accept. And if I have A, B, B, I could go from Q1 to Q2 on the A's and then back from Q2 to Q1 to Q0 with the B's and accept. And if I have 3 A's and 3 B's, it would be Q0, Q1, Q2, Q3. And then the B's would bring me back from Q3, Q2, Q1, Q0. What's the problem with that line of thinking? How many states do I need?
You'll still need as many states for however many like A's and B's you have. It's like you said, you don't have any memory, so you can't.
Exactly.
A's and B's
So
you have.
exactly. And since I haven't put an upper bound on n, then I need an infinite number of states. And it's called a finite state machine for a reason, right? Finite number of states. Now, if I limit n, what if I said n was equal to 100? Then you could do it. You could do it that way. But why? Because the language is finite, big, but it's finite, and every finite language is regular. Because we can brute force the finite state machine, but we can't do it here. So we need to keep track of how many A's we saw, and that's what the stack is going to do. Now, interestingly, we do not have any limitations on the stack. We have a potentially infinite number of items can go on our stack. So we can keep track of a potentially infinite number of A's. And you can imagine just intuitively how this might work. I'm going to start processing the A's, and every time I see an A, I'm going to toss a symbol on the stack. And then when I see B's, I'm going to remove a symbol from the stack. And by the time I get done with the string, if I see that I have the empty stack symbol there, I must have had the same number of A's as I had of B's, and I would accept. If I have more A's than B's, I won't see the empty stack symbol. If I have more B's than A's, I'm going to get to the empty stack symbol too soon while I'm still processing B's, and I would immediately reject. All right, so here's how that machine looks. They end up, by the way, if you accept by empty stack, you often don't need very many states at all. I think I could have done this with one state, but I chose not to. No, I needed to get to that other state because I needed to take care of the B's. So here's all I do. I start in Q0. Notice I have no accepting states because I'm going to accept by empty stack. I start in Q0, and if I see an A and a $sign, in other words, the first thing I see is an A, and I'm at empty stack, so I see a $sign. I'm going to stay in Q0, and I'm going to push $0 on stack. Now, this is a notational thing, and if you really want to do it the other way, that's okay, but you're going to have to explain it to what you're doing. I'm pushing $0 on the stack. Why do I push it in that sequence? I push it in that sequence because remember, stacks have LIFO behavior, last in, first out behavior. So if I push $0 on the stack, how is it going to look on the stack? The bottom element is the $sign, and then the top element is the 0. So basically, the first thing I see in the string needs to be an A, because that's the situation where I'm in the start state, an empty stack, then I see an A, then I stay in Q0, and I put $0. So I've seen one A and I have 1 0 on the stack. And then if I have a 0, in other words, I see that there's a 0 on the stack and I'm still processing A's, I add another 0 to the stack. Now, why am I adding 2? Remember, we popped one of them. So now in order to add 1, I need to put the original one back and another one. So as long as I'm processing A's, every A I see, I throw a 0 on the stack. And then at some point, I'm going to start to see some B's. And so the first time I see a B, I should have a 0 on the stack. If I see a B with a $sign on the stack, what does that tell you? What does that mean? I'm in state 0, and I see a B, and there's a $sign on the stack. What does that mean? Garbage state, right, but why? Why? I mean, what does that mean in terms of the string? Maybe that's a better question. What does the string look like? You're exactly right, because of my machine, it goes to the garbage state, yeah. But in terms of the string, if I'm in Q0 and there's a $sign on the stack and I see a B, what can you tell me about this, how that string was constructed? Anything? Right, exactly. It started with a B. If I'm in state 0 and I have a $sign on the stack and I see a B, what that tells me is the first symbol of the string was a B, and that's not allowed. So the only transition that makes sense if I see a B is I better have at least one 0 on the stack, meaning I've seen at least one A prior to that. So here I am with a B. I see a 0 on the stack. Remember that 0 got popped. And so now I'm going to transition to Q1. And the reason that I like to transition to Q1 is because now if I ever see any more A's, that should trash the string. So now that I'm in Q1, all I can accept is B0. If I did that over here, I could accept B0 and A. I could still see A0 again, which would be a violation of the rule. So over here in Q1, all I'll accept is B0, and I put nothing back on the string. So what's happening? Remember, every time you're popping the 0, popping, you're popping that off the stack. So every time you see a B, you're removing a 0. So over here, every time you see an A, you're adding a 0. And over here, every time you see a B, you're removing a 0. So when you're done processing the string, if you're back to empty stack, it must be that the number of A's was equal to the number of B's. Now, once I draw this picture, and it only took me 5 times because I kept making typos, then it's the same trick as before. You do your transliteration over into the 7 tuple. So Q is just the 2 states, sigma is AB, that was defined. Gamma, I said, was going to be 0, 1, and $sign. Notice I never used the 1. Q0 is Q0. I'm using the $sign as my empty stack sign. I have no accepting states. And my delta is more complicated, so I made a little Excel page to do it. Are we adding empty string to the stack? You start with empty string. Empty string to the stack. Are we adding? No, you don't add empty string to the stack. You can add empty stack symbol to the stack, right? The $sign is the empty stack symbol. And you always start out with the empty stack symbol in the stack. Now, what I did here, since I popped it off, the first AI process popped it off, I put it back. Now, what you are not allowed to do is, no matter what, at the end, just pop that. You know, you've got a big stack with 1,000 elements in it, and then you push the empty stack symbol on top and say, ta-da, what is the lambda transition? Okay, that's my way of saying the string that I'm adding to the stack is nothing. I am not putting anything back on the string, on the stack. I popped this 0 and I'm putting nothing back. Whereas here I popped the empty stack symbol, I put it back plus a 0. Here I popped a 0 and I'm pushing a 0 back and pushing another one back. But when I see a B, I need to remove them. So for B0, I don't want to put anything back because I want that 0 permanently removed from the stack. Did that help? Okay. All right, so the delta function, I'm going to let you go in just a second, and we'll pick this up on Wednesday. The delta function gets a little uglier. This part here is the state transitions, and now I have to do it in pairs. This is A, empty stack, A0, A1. I need to have a situation for each one of these. And again, what I did is whatever is not represented on my graph, I'm just going to say is a reject. So I'm just going to put a big R there and pushed on the stack. If I rejected the string, then it doesn't matter what happens to the stack. It's NA. And so I have a more sophisticated, more cluttered, maybe more than more sophisticated, a more cluttered version of my transition function. But it's still the same basic idea. You have state transitions, but now we have to talk about what we're putting on the stack. And again, this comes directly from the graphic that you did. Okay, I'm gonna let y'all go. We'll do this example again on Wednesday and pick up the second example. And then by then I should have some sample problems available to you that we can play with. Okay?
Thank you, Professor.
Cool.
Thank you guys. Y'all have a wonderful day.